Hello friends, welcome to engineering tutorial. So in today's video we are going to study about capacitors connected in series. We are going to study about both capacitors connected in series and parallel. First we are going to discuss about the capacitors connected in series. We are going to see the expression, mathematical expression for equivalent capacitance of series combination of capacitors, and we are going to mathematically derive that expression later on. So as you can see in this circuit diagram, we have a number of capacitors C1, C2, C3 up to n number of capacitors which are connected in series across a voltage source V. Now you can say that these capacitors are connected in series because there is a end-to-end connection pattern. It means one of the end of the capacitor is connected to the other end. The right end of capacitor C1 is connected to left end of C2. The right end of C2 is connected to the left end of C3, and so on. And all these capacitors which are connected in end-to-end fashion are connected across the voltage source V. And the current flow through the series combination of capacitors is small I. The same current I flows through each of the n connected series capacitors. Okay. Now, the equivalent capacitance or the total capacitance of this combination of n capacitors is given by this expression, 1 by C equivalent, where C equivalent is the total capacitance of this combination, is equal to 1 by C1 plus 1 by C2 plus 1 by C3 plus 1 by Cn, up to if there are n number of capacitors. So it is the reciprocal of the individual capacitances. Okay, they are connected in series, but the expression is like this. So it can sometimes create confusion in the mind of students because they are mostly used to this expression for parallel combination. In case of resistors, in case of inductors, this expression is for parallel combination of the circuit elements. That is, if the resistors or inductors are connected in parallel, then this expression gives the equivalent resistance or equivalent inductance for the parallel combination. But in case of capacitors, it is the opposite. When the capacitors are connected in series, the equivalent capacitance is like this: 1 by C equivalent is equal to 1 by C1 plus 1 by C2 plus 1 by C3 up to 1 by Cn, which is the reciprocal, in reciprocal form. Okay, so always remember, in case of capacitors, when the capacitors are connected in series, the equivalent capacitance is given by the reciprocal of the individual capacitors. Okay, so now we are going to mathematically derive this expression. So now we are going to derive the mathematical expression for the equivalent capacitance of series combination of capacitors. So we are using the same circuit diagram which consists of n capacitors connected in series across a voltage source V with the circuit current or the series current I flowing through each of the n capacitors. Now here Vc1, Vc2, Vc3 and Vcn are the voltage across the respective capacitors C1, C2, C3 and Cn. Okay. Now pay attention to the polarity that it has been mentioned, plus minus, plus minus, plus minus, plus minus, because current always flows from positive to negative terminal of the capacitor internally. Okay, because capacitors, inductors or resistors, they always absorb power from a voltage source. Okay, that's why this sign convention is used. Okay, so if we KVL in this loop, in this closed loop, we will get V is equal to Vc1 plus Vc2 plus Vc3 up to Vcn. Now we know that we have already studied in my previous video that the voltage across a capacitor is given by this formula, this expression, 1 by C minus phi to t Ic dt. That is the reciprocal of the capacitor multiplied with the integration of the capacitor current from limit minus phi to t. Here minus phi is used because capacitor is capable of storing energy, and we have to include the past state, the past stored voltage of the capacitor. That's why this expression is used. Okay, so this is the expression for capacitor voltage. So we are using the same here. Here this V is the total voltage or the applied voltage. Now this can be given by the expression of 1 by total capacitance, which is the equivalent capacitance C equivalent, with the integration of the circuit current minus phi to t dt. For total voltage, total capacitance is used, and for the individual capacitor voltages, individual capacitors are used. So Vc1 is 1 by C1 minus phi to ti dt, Vc2 is 1 by C2 minus phi to ti dt, Vc3 is 1 by C3 minus phi to ti dt, and Vcn is 1 by Cn minus phi to ti dt. Now you would be noticing here that the current in each of the expressions is the same. Because it is a series connection, the current flowing through each of these capacitors will be the same. It will be I. Okay, we have taken the circuit current as I. The series current will be the same in each of the capacitors, C1 up to Cn. So from this expression, we can take minus phi to ti dt as common from both the LHS and the RHS. Okay, so we have done that. We have taken minus phi to ti dt as common from both the LHS and the RHS. So if we cancel this out from both the LHS and the RHS, we can see that 1 by C equivalent is equal to 1 by C1 plus 1 by C2 plus 1 by C3 plus 1 by Cn. This is the expression for equivalent capacitance for series combination of capacitors. Okay, so we have derived the expression 1 by C equivalent is equal to 1 by C1 plus 1 by C2 plus 1 by C3 up to the nth capacitor, the reciprocal of the nth capacitor. So simply we put KVL in the loop, then we express the total voltage in terms of the total capacitance or the equivalent capacitance, and the individual capacitor voltages in terms of the individual capacitances using this formula for capacitor voltage. Then we took minus phi to ti dt common because the circuit current I is the same in each of these capacitors, and we cancelled it out from both the LHS and the RHS, which left us with 1 by C equivalent is equal to 1 by C1 plus 1 by C2 plus 1 by C3 up to the nth capacitor reciprocal. So this is the expression, the derivation of the mathematical expression for equivalent capacitance of series combination of capacitors. Next we are going to study about capacitors connected in parallel. So now we are going to discuss about the parallel combination of capacitors. So here you can see there are 3 capacitors which are connected in parallel across a DC voltage source V. So you can say that these 3 capacitors are connected in parallel because the left ends of the capacitors C1, C2 and C3 are connected at one common point, and the right ends are connected at one common point. So at both the common points are connected to the positive and negative terminals of the voltage source V. Okay, and they are connected one above the other. It means that in parallel connection, the voltage across the capacitors C1, C2 and C3 will be the same. Okay, it will be V volt. The voltage across C1 will be V volt, the voltage across C2 will be V volt, and the voltage across C3 will be V volt. And the total circuit current I gets divided into the individual capacitor currents I1, I2 and I3. Now the equivalent capacitance of this parallel combination of capacitors is equal to C equivalent is equal to C1 plus C2 plus C3, which is simply the sum of the individual capacitances. So this is similar to the equivalent impedance or the equivalent combination of resistors and inductors connected in series For resistors and inductors connected in series, there is a similar expression. R equivalent is R1 plus R2 plus R3. L equivalent is equal to L1 plus L2 plus L3. But here, this expression is for parallel combination of capacitors. Okay, so the behavior of the capacitors is opposite to that of resistors and inductors with respect to the equivalent impedance or the equivalent capacitance. Okay, it is the opposite. So never get confused that when the capacitors are connected in parallel, the equivalent capacitance will be 1 by C equivalent is equal to 1 by C1 plus 1 by C2 plus 1 by C3. That is for series combination of capacitors. So that can sometimes cause a mistake. So please be careful about that. Now we are going to derive the mathematical expression of this equivalent capacitance. How we got this expression? So let's see. Next, we are going to derive the expression for equivalent capacitance for parallel combination of capacitors. So in this circuit diagram, you can see that three capacitors C1, C2 and C3, they are connected in parallel across a voltage source V. You can say that they are connected in parallel because all the left ends of the three capacitors are connected at one point and all the right ends are connected at one point, and these two common points are connected across the two terminals of the voltage source. Small I is the total current flowing in the circuit, which gets divided at this point into I1, I2 and I3, which flow into capacitors C1, C2 and C3 respectively. So if we put KCL, Kirchhoff's current law, at this node, we will get I is equal to I1 plus I2 plus I3. Now we know that the current flowing through a capacitor is given by this expression. Okay, the capacitor current IC is equal to C dVc by dt, where Vc is the voltage applied across the capacitor. Here, as the three capacitors are connected in parallel, the voltage across them will be constant. It will be the same. It means the voltage across C1 will be V, the voltage across C2 will be V, and the voltage across C3 will also be V. This will be constant. The voltage across C1, C2 and C3 will be V volts. So we can write the total circuit current I in terms of the total capacitance or the equivalent capacitance. Let's say the equivalent capacitance is C equivalent, Ceq. So I is equal to Ceq dV by dt. So we replaced or substituted I with this expression, C equivalent dV by dt, where V is the applied voltage. Now, the individual capacitor currents I1, I2 and I3 are expressed in terms of the individual capacitances C1, C2 and C3. I1 is equal to C1 dV by dt, I2 is equal to C2 dV by dt and I3 is equal to C3 dV by dt. Now you can see in both the LHS and RHS of this expression, dV by dt is common. Okay, so if we take dV by dt from this expression, we get C equivalent dV by dt is equal to C1 plus C2 plus C3 into dV by dt. So if we cancel out dV by dt from both the LHS and the RHS, we are left with C equivalent is equal to C1 plus C2 plus C3. If there are n number of capacitors, then it can go up to n, the nth term. So in case of parallel combination of or the parallel connection of a number of capacitors, the equivalent capacitance is simply the summation of the individual capacitances. So never get confused that this looks similar to series connection expression for resistors and inductors, so it will be the expression for series connection of capacitors. That's where the most of the time mistakes happen. It is the opposite in case of capacitors. In case of capacitors, for parallel connection, the equivalent is in terms of sum of the individual capacitances. In case of series connection of capacitors, the equivalent capacitance is in terms of reciprocal of the individual capacitances. That is 1 by C1 plus 1 by C2 plus 1 by C3 up to 1 by Cn is equal to 1 by C equivalent, which we just studied previously. So never get confused. The behavior of capacitors in terms of equivalent capacitance is different from resistors and inductors, actually the opposite. Okay, so here we have derived the expression for equivalent capacitance of a number of capacitors connected in series and parallel, both. So I hope you like this video, and please subscribe my channel Engineering Tutorial for more such videos related to electrical, electronics, instrumentation and communication engineering. Have a great day. Thank you very much.